This session is a little bit of history is being made, in the sense that the recording right at this moment is being done in high definition, not standard STD definition. A friend of mine, in fact my son-in-law, who has a master's in computer science, a very practical turn of mind, whereas I'm more the theorist and not an engineer at all. Anyway, he and I have been playing around with compression programs so the idea is to record directly in high definition and then compress them and then send a compressed file, upload to YouTube and have a look. And so yesterday, for the first time, we uploaded these compressed files to see how they look, and they look fine. So now, instead of doing just a dummy Mickey Mouse file, a very short length, do a full session. So this is the first, and if it's successful and the file itself is not too long, so I'm still not too sure about that, well, just keep doing it, and then perhaps keep the readability, but decrease the size of the file in absolute size, because the bigger it is, the longer it takes to upload to YouTube. And it's taking me 4 or 5 hours for 10-12 minutes of filming. So that's still a bit of a problem. Alright, well, from last session, just starting on our very first solution of the time-independent Schrödinger equation. And in this section we'll actually do it, finish it, our first one of many. So you'll really have got the habit of solving these equations, these time-independent Schrödinger equations, by the end of 4 chapters, because the next 4 chapters are on this topic, including, well, the math is a bit harder, but a real-world case. Not like this one is a bit artificial, but it's more to illustrate the techniques than anything. But a bit later we will solve a real case using these kinds of techniques for the hydrogen atom. Okay, all right. So our very first one, it's called the infinite square well potential, and I hope all this is coming up very nicely now in high D, although compressed high D. Of course, when you compress something, you lose quality to some extent. But if what you start with is high quality or high definition, hopefully the final result will still be more readable than it was when it was filmed in standard, which is a lot lower resolution. Okay, so this case is called the infinite square well potential, and you may remember from the previous session the potential either side, so here's your x-axis, here's the origin. So at minus A and A are infinite barriers, impenetrable. Wave equals cannot get into them. The potential is just infinite. So absolutely barred for x greater than A and for x less than A. So these two regions here, the particle cannot be in. So the wave function then is 0, right? When you square it to get the probability density, well, that probability density is just going to be 0 in these two regions. The particle just cannot get there. It's impenetrable. All right. So the action takes place in this region here, between plus and minus A. All right. And in this region, you're told that the potential is 0. Okay. But the potential V is infinite here and here. Okay. So that's the specs. And you're asked to find the energy levels, in this region, well, in this strip, if you like. It's a one-dimensional problem. So between minus A and A. Right. So you solve the time-independent Schrödinger equation, which I've written here again to remind you. Okay. And I've also, again, as a reminder from previous session, there are conditions that you place on your psi function. In this case it'd be u, because we're dealing with the time-independent form of the Schrödinger equation. So when you see psi, you can just replace it with u. u is the part of this psi function that depends only on position, on x. All right. Well, that function, that wave function, must be single valued, normalizable, and psi and the first derivative of psi both need to be continuous. Right? They were the conditions we thought were reasonable from last session. Okay, so that also a bit of revision. Okay, so let's actually start solving the equation. Now we know u is 0 in these two regions. It can't be there because these regions are impenetrable. It cannot be penetrated, cannot be got into. So all the action is taking place within this region plus or minus a. All right. So let's deal with this region. So we have our time-independent Schrödinger equation, and in this region here, this strip, v is 0. Okay. So this simplifies down to this, and now you've just got. And remember, u is only a factor of x here. So you don't need to write down the partial differential. There's only one variable in u, so you can use the formal a differential, not a partial differential. Right? Just d by dx. In this case, d squared dx squared. Okay, so you just solve this equation. And I was saying in the previous session, solving Schrödinger's equation to a large extent boils down to just solving DE's differential equations. Okay, so solve this DE, right? In the case, in this region here, where V is 0. All right, well, let's see. So divide both sides by all this, well, h bar squared over 2m, and then let alpha be the square root of this. Now, yeah, why are you doing that? Well, the usual thing, it works, but you've got a second order differential here, and that typically is of this. The solution to it for u is of this form. It'll be a sine cosine type of combination, right? And if you let alpha be this, if you differentiate u twice with respect to x, you'll get a minus alpha squared outside here, which corresponds to your e and your h bar squared, well, to this. Right? Okay, so that's where the alpha came from. I assume you've done enough, that you have enough experience in calculus to know how to solve a differential equation like this. It's sort of undergrad, well, even fresher level, I think. Okay, so I assume you know how to do that, right? So u is of this general form: a sine plus b cos, blah blah, and u will be 0 in these two regions, right? So now we've got a solution in general form. It's not very specific yet, but at least we have the form of a solution. U will take this form in this region. All right. Okay. Now we've got the general form here. We can now start using these constraints, these conditions on u. Well, one of them is that u is continuous, right? So at the boundaries, like here and here at a and minus a. Now we know u is 0 here, so infinitely close on the right-hand side of this barrier at x equals a, we know that u is 0, right? So that means infinitely close on the left-hand side of this barrier a, u here must also be 0 to have continuity, okay? So that's where this 0 comes from. So at x equals plus a, this u here must be equal to a, must be continuous. Okay? No jumps, no cuts. So this here must be equal to 0 at plus a. Now with the same logic, it must also, u must also be 0 at minus a. So you plug in x as minus a here, and you'll get this. Okay. Now, all right. Now we're a step further. Now you may remember from the previous session talking about imposing these constraints actually causes, in a sense, the energy levels to be discrete. Well, now it's starting to happen, because watch. for this to be 0, this to be 0, it means that A, let's see. So if A is 0, so if A is 0, there's two solutions to this, two distinct